This discussion goes into some further detail on hydroplate theory's explanation for the origin of asteroids, comets, and Trans-Neptunian objects, or TNOs. Rather than repeat information that has been covered in Part 2 of the overview series, I'll simply delve into this side topic. So you may wish to review the end of Part 2 of the overview presentation to get the introductory info on why asteroids, comets, and TNOs are very unlikely to be the building blocks of the solar system, and see the many telling evidences that point to the Earth itself as the most likely origin for these objects. This presentation provides more information on the origin of meteorites and a more detailed explanation for why hydroplate theory says that rocks and water in the fountains of the Great Deep later merged to become comets, asteroids, and TNOs, and how those bodies after they formed ended up in their present orbits. Finally, we'll review how the moon's scarred surface is actually evidence of this powerful launching of material from Earth. Notice that the hydroplate theory is not saying that asteroids, comets, and TNOs came fully formed from the Earth. Rather, these bodies formed in the weeks, months, and years after the flood began from the rocks, water, gases, and other compounds launched into the inner solar system by the fountains of the Great Deep. Of course, some ejected bodies did not combine to form larger bodies. These smaller, rocky, sometimes metallic bodies are called meteoroids. Those that have returned to Earth's surface are meteorites. Studies reveal that meteorites contain a variety of surprising materials which have experienced a unique and turbulent past. The following items have been found in meteorites: chondrules, salt crystals, water, limestone, which only forms in liquid water, DNA components, possible cellulose, sugars, living and fossil bacteria, terrestrial-like brines, excess left-handed amino acids and heavy hydrogen, and Earth-like minerals and Earth-like isotopes. All these implicate Earth as their source and the fountains of the Great Deep as the powerful launching mechanism. Meteorites can be divided into three classes. 95% are stones, rich in silicon and the mineral olivine, both common on Earth. 4% are irons, which are an iron-nickel mixture that was initially molten and experienced uniform heat of at least 1300 degrees Fahrenheit, as evidenced by their unique Widmanstatin pattern. Finally, 1% are an intermediate class of stony irons called pallasites. Pallasites formed from a molten iron-nickel mixture which seems to have been injected into or mixed with fragments primarily of olivine. The mixture of metal encasing olivine and other rocky minerals is surprising because the iron-nickel alloy is twice as dense as the minerals. The metals were molten when they solidified around the stones, but the less dense stones should have quickly floated to the top. Just as you would expect ping-pong balls to float on the surface of a bucket of water. But what if you found the balls frozen within the water? Pallasites are just as surprising. It has been proposed that pallasites are fragments of an imagined large asteroid that had a molten metal core which was pressed into the rocky crystals at the core mantle boundary. Later, this asteroid is imagined to have catastrophically broken up, releasing the pallasite mixture of iron and rock fragments. If this were the case, cooling rates of all these fragments would be uniform. However, research on 8 different pallasites concluded that the molten iron-nickel mixtures cooled at such diverse rates that they could not have originated at a core mantle boundary, even in an asteroid. There are other problems with this idea. Asteroids are not strong, dense rocks that would become molten if struck in the necessary high-speed impact that is imagined to have created the molten condition in the first place. Rather, asteroids are fragile, low-density floating piles of rock loosely held together by water ice. An asteroid will not develop a molten core if a meteoroid slams into it. Remember, asteroids are flying rock piles, so a large impact will scatter the rocks that make up the asteroid. Besides, asteroids are extremely cold, and because they are so much smaller than a planet, they lose their heat much faster. So in light of these physical challenges, the scenario that would get an asteroid to melt such that it would produce much less support a molten core seems very unlikely. Finally, pallasites contain remnant magnetism, yet there is no hard evidence that any asteroid ever had a magnetic field, although many hold to that idea. Of course, Earth has a powerful magnetic field, and as my other video on the origin of Earth's radioactivity shows, powerful electromagnetic discharges were released within the crust at the time of the flood. Hydroplate theory poses a much different scenario explaining the formation of pallasites. Tidal pumping from the moon and the sun stretched and compressed the pre-flood Earth's pillars twice a day. For centuries before the flood, the heating from this cyclic compression and internal friction within the pillars heated the materials in the subterranean chamber. After a decade or so, the subterranean water became supercritical and ate into the pillars, making them porous and brittle. Due to gravity, over time, dense metals with lower melting points than rocky minerals slowly migrated through the now porous structure toward the pillar's base. Once the crust was ruptured, the pressure in the supercritical water under the crust began to drop. Remember, most of the weight of the plates was supported by the pressurized waters. So as the water pressure dropped, the pillars had to support more of the crust's weight. The pillar material was crushed under the added weight. The friction from small slippages in the failing pillars melted materials at points all along the fractures. The melted material then acted as a lubricant, which encouraged further slipping and melting of nearby material. Rather than slow migration through tiny pores, the many fractures became conduits which more quickly sorted materials due to gravity. Dense liquid iron and nickel moved down toward the pillar bases, while low-density materials and minerals that melted like quartz and trapped supercritical water were displaced and migrated upward along the same faults. Fractures in the crushed rocky minerals at the pillar's bases became engorged with molten iron and nickel. As the plates above began to slowly flutter due to the movement of the escaping supercritical water, these fractures received powerful high-pressure injections of molten material from above. The fractured solid minerals, which were lower in density and had higher melting temperature, were further pulverized as liquid metal began to pool at the bases under extreme pressures. As the amplitude of the fluttering crust above increased, the pillars were lifted from their bases in tune with the crust's oscillation. Pooled metals and stony minerals encapsulated in liquid metal were quickly swept into the flow toward the ejecting fountains. As the pillars oscillated down, they were slammed back into the mantle bases. Pressure spiked more. Crushing, melting, and injection of iron and nickel into the bases occurred. Quartz and other minerals with piezoelectric properties discharged as the pressure waves rippled through the buckling pillars. At points, powerful electrical discharges pinched nuclei together in small fusion events, which melted surrounding materials, forming chondrules within some of the rocky matrices. These same discharges subjected the surrounding materials to intense magnetic fields as they were forming. This and the Earth's magnetic field explain why pallasites are found to have remnant magnetism today. For more detail on the physical mechanism that resulted in these fusion events and chondrule formation, refer to my other video titled The Origin of Earth's Radioactivity. Hot fragments of crushed pillars and mantle bases were chaotically tumbled and accelerated by the rushing supercritical water toward the open ruptures in the crust. Reaching the base of the ruptures in the thick crust, the fragments were further pulverized and tumbled in the flow, which greatly cooled as it accelerated out and experienced free expansion into the vacuum of space. In a matter of seconds, material experienced rapid thermal shock from the extreme heat under the plates to the extreme cold in the expanding flow into the equally cold vacuum of space. The metals quickly solidified around the slurry of stony minerals, trapping and freezing around them, forming a unique matrix of dense metal and mineral crystals. The chaotic tumbling and rapid ejection into the weightless vacuum of space explains why the low-density minerals were unable to separate from the dense metal matrix. These events also explain how molten chondrules formed within some stony pillar fragments, due to powerful electrical discharges. Intense uniform heating of the iron-nickel alloys under the pillars explains iron meteorites' unique Widmanstätten crystalline pattern. The many variables at play as the plates and the fountains pulsed, such as the distance from a given pillar to the nearest rupture point or the intensity of a fountain pulse, made for much variability in the rate that ejected fragments cooled. Therefore, hydroplate theory's mechanism of formation simply explains why different pallasites are found to have cooled at very diverse rates. They did not come from an imagined asteroid's unlikely core boundary. They came from Earth. This, of course, explains why meteorites share so many Earth-like materials and properties. We'll now focus attention on comets, asteroids, and TNOs. Remember that comets are loose collections of ice, dust, and small rocky particles. Asteroids are small minor planets that revolve around the Sun, with orbits lying chiefly between Mars and Jupiter. And a Trans-Neptunian object, or TNO, is any minor planet in the solar system that orbits the Sun at a greater average distance than Neptune. To understand the origin of these objects, we first should cover how objects fall in a gravitational field. In other words, how objects orbit each other. If you were on a tall mountain and fired a cannon, you'd expect the ball to travel some distance and then hit the ground as gravity pulls the ball down. If you added more and more cannon powder, the ball would travel further and further, yet gravity would still pull the ball down. If you could trace the path of the ball from the side as we are viewing it here, you'll notice that the arc shape of the path of each successively faster shot more and more closely matches the circular shape of Earth. If you could get the cannon to fire the ball at around 17,000 miles per hour, then the ball's falling arc would match the curvature of the Earth and the ball would simply continue to fall completely around the Earth and never come down. This is circular orbit. If you could fire an object even faster than this, the object would enter an elliptical or egg-shaped orbit and travel far from Earth. Objects fired far from Earth will eventually become captured by the Sun's gravity and they would then orbit the Sun rather than the Earth. The object would travel progressively slower as it traveled further and further along the elliptical path until it reached the furthest point in its orbit, called its aphelion. Then, as gravity pulled it back, the object's speed would again increase as it fell back toward the Sun, where it would be the nearest to the Sun and traveling the fastest. This is called the object's perihelion. If you could fire the object even faster, the elliptical orbit shape would become more and more eccentric, until another threshold is reached, which is called a parabolic orbit. Parabolic orbit is the dividing line between closed elliptical orbits and open or hyperbolic orbit. If the object were traveling any faster, it will enter open or hyperbolic orbit, meaning that it is not really in orbit around the Sun anymore and will never return. In other words, the object travels at a high enough initial velocity that even though it slowed as it moved away from the Sun, it moved so far away, so rapidly, that the Sun's gravity out at would-be aphelion for the object is too weak to pull it back. So the object escapes the Sun's sphere of influence out to infinity. Some comets have been observed to be on just barely outbound open orbits. However, no comet has ever been seen falling toward the Sun on an open orbit. This is an important point when we consider what we've been taught to believe about comet origins. What do we observe today? There are just over 1,100 comets whose orbital parameters are precisely known, and around 2,300 more comets have been observed, but not long enough to determine orbital parameters. Some of these observations may be of the same comet at different times. The streams of dust and gas released by a comet form a huge, extremely thin atmosphere around the comet called a coma. A common property of all comets that have been inspected more closely is that they are made up of a loose collection of ice, dust, and surprisingly well-rounded rocks. The density of each comet's nucleus is extremely low, about that of foam, talcum powder, or a meringue on a topping of a pie. So despite their dust and gaseous tails being sometimes larger than 1,000 Earths, comets have very little mass. Most cosmologists agree that the source of most comets must be a cloud of material termed the Oort cloud, composed of trillions of comets in a spherical shell surrounding the solar system. A cloud so far away that no one has ever seen it or detected it in any way. Carl Sagan has admitted, and I quote, "Many scientific papers are written each year about the Oort cloud, its properties, its origins, its evolution. Yet there is not a shred of direct observational evidence for its existence." So in spite of much speculation, not one new inbound open-orbit comet from the imagined Oort cloud has ever been observed. However, many comet deaths or disintegrations have been observed. One of the main contributors to comet deaths are the planets themselves, mainly Jupiter, the most massive planet. Comets with aphelions that lie near Jupiter's orbit, like comets A and B shown in the animation, will be greatly affected by Jupiter's gravity. These comets are part of a group called Jupiter's family. 60% of short-period comets are in Jupiter's family. Unfortunately, short-period comets have been arbitrarily defined as comets with periods less than 200 years. A more physically meaningful definition used here will be comets with periods less than 100 years, because there is a huge recognized excess of such comets. So any acceptable theory of comet origins should explain the excess comets with periods of less than 100 years. Surprisingly, simulations show that comets in Jupiter's family will last only about 12,000 years before they collide with a planet or Jupiter's gravity rips them apart, or flings them out of the solar system. In 1992, we all saw Jupiter rip comet Shoemaker-Levy 9 into 21 pieces that one orbit later collided with Jupiter. A question immediately arises. Where did the current crop of short-lived comets come from if these have supposedly been around for billions of years? Extrapolating these comets' short 12,000-year half-life back in time to billions of years ago will indicate that initially there must have been an unrealistically large number of comets in Jupiter's family. How is this explained? Or from this data, should we consider if this doomed small population of comets was actually produced recently about 5,000 years ago as a result of the flood? This would readily explain why many comets have managed to survive today in such a deadly environment. We've been taught the Oort cloud theory, which attempts to explain the origin of comets. The distance from the Sun to the Earth is defined as 1 astronomical unit, or 1 AU. The Oort cloud has never been seen or detected in any way, but it is imagined as a shell of comet materials that are dispersed about 50,000 AU from the Sun. As I've already mentioned, it's curious how several outbound comets have gained enough energy from interactions with the planets to be flung out of the solar system. However, astronomers have never confirmed a single inbound comet in open orbit from the imagined Oort cloud. This is a troubling lack of evidence for the Oort cloud theory and leaves open the problem of explaining how comets have supposedly existed for billions of years while planets like Jupiter have been rapidly vacuuming them up. Hydroplate theory proposes that the material that later merged to become comets, asteroids, and TNOs was launched during the flood. In part 1 of the overview series, I've already discussed how their physical and chemical components are very similar to the materials and conditions found on Earth. In fact, some of those materials, like amino acids and complex organic compounds, are uniquely concentrated and abounding on Earth. Hydroplate theory looks at 3 orbital properties of comets that can be tied to the components of relative motion that all comets received from the Earth's orbit. Observed comets are distinctively grouped as follows. For each group of comets, we will review their properties and see how they relate to how rapidly they were ejected from the Earth. A comet's orbital period is the time it takes a comet to complete one orbit around the Sun. Obviously, Earth's orbital period is 1 year. Next is the comet orbit's angle of inclination, which is the angle of the comet's orbit measured from the Earth's orbital plane. Finally, the orbit direction is defined as either in the prograde direction if the comet is orbiting in the same direction as Earth orbits the Sun, or retrograde if the comet is orbiting in the opposite direction as Earth. Today, at least 1,118 comets with calculated orbits have been identified. Their orbits can be grouped into 3 categories of short, medium, and long orbit periods or cycles. About 729 comets have periods of 100 years or less, and only 102 comets with medium periods of 100 to 700 years, while 287 comets have periods that exceed 700 years. We will next look at how hydroplate theory explains the existence of short, medium, and long period comets. First, we will discuss the concept of relative motion. Imagine you had marked 3 lines on the ground next to a rail track. Imagine a train comes down the track at 100 miles an hour, and assume that the moment the train passes your lines on the ground, 3 balls are launched backward from the train cars at the same angle. The only difference is the balls are launched at different speeds. The ball tossed at only 50 miles an hour in the backward direction would actually hit the ground well forward of the point it was thrown from because the ball was traveling on the train at 100 miles an hour. So because it is so slow, most of the green ball's trajectory matches the direction and speed of the train, even though it was thrown at a rearward angle. We could say that the motion of the green ball has a noticeable signature imprinted on it by the train's trajectory. The 150-mile-an-hour ball pitched at the same angle would still fall forward relative to the ground. However, you can see that the yellow ball's path is less affected by the train's speed and direction than the green ball. The train's relative motion signature on the yellow ball is less pronounced than that of the green ball. Finally, if you fired the red ball at 500 miles an hour at the same backward angle from the train, the ball would finally land at a point behind the line on the ground because the train's relative motion does not affect the red ball's overall trajectory nearly as much as it did with the yellow and green balls. The train's trajectory signature is very faint for the red ball. Now imagine you threw many balls at 50 miles an hour, each at a random different angle. What would you expect? Well, we'd find that for all the green balls, the train's contribution to the velocity is so dominant that every one would land in front of the line on the ground no matter which angle you threw them. Now repeat this thought experiment for the faster yellow balls. The change of velocity plays a lesser role, so only a small percentage of the balls pitched directly rearward would actually land behind the line on the ground. And finally, the change speed and direction play only a minor role in affecting the balls fired at 500 miles an hour. So if we repeated the experiment at the final time for them, we would see that a more equal percentage of balls land on either side of the line on the ground. If you increase the speed even more, the percentage aft versus forward of the line would near 50-50. Now let's use this discussion to see how a similar signature of Earth's relative motion can be seen in some comet trajectories and not so much in others. Short-period comets are like the green balls. They have short orbit cycles, so they were not ejected at as high a velocity from their source. So the Earth's orbit signature is readily seen in several ways. The orbit angles are very slight and do not stray much above or below Earth's orbital plane. Very interestingly, 97% of all short-period comets are prograde. They orbit in the same direction as Earth. Medium-period comets are like the yellow balls. They were ejected at higher velocity from their source, so the Earth's orbital signature can be seen, but is less pronounced. The speeds are high enough that orbital angles of inclination are dispersed in all directions. But only 58% of medium-period comets still maintain the same prograde orbital direction that Earth has. 42% were launched with enough energy and at just the right angle to have taken a retrograde orbit. Long-period comets are like the fast red balls. They were ejected at the highest velocities from their source, so the Earth's orbital signature is not readily seen in this family of comets. Again, the orbital angles are dispersed in all directions. In addition, the orbit directions for long-period comets are pretty evenly split, just about 50-50 between prograde and retrograde, as we'd expect with the spinning Earth randomly firing these objects at extreme velocity. Next, we will focus on asteroids. According to hydroplate theory, the ejected clouds or swarms of materials that later formed into asteroids would have most likely entered an elliptical orbit with the Sun. Why, then, are most asteroids not in comet-like orbits? Why are most asteroids shown as white dots in this picture in nearly circular orbits concentrated in the donut-shaped asteroid belt between the orbits of Mars and Jupiter? Shouldn't some asteroids have high angles of inclination? A puzzling question then arises when we look at the asteroid belt today. Most asteroids shown as white dots have a near circular orbit between Mars and Jupiter. If hydroplate theory is correct, how did asteroid orbits become circular and expand out beyond Mars and Jupiter? Even more puzzling, how did large asteroids become TNOs far beyond Neptune's orbit? Also, per the hydroplate theory, this ejected material would have been launched from Earth in many random directions and highly inclined angles. This would tend to produce more of a spherical asteroid shell. Yet the asteroid belt has a donut shape and is centered near Earth's orbital plane. So how did ejected materials with highly inclined orbit angles change to become asteroids concentrated near the orbital plane? There were several special conditions immediately after the flood that produced several persistent but powerful forces due to energy from the Sun. The first is the radiometer effect. You can do a YouTube search and find many videos and explanations of this effect of light, which energizes gas particles and acts to move solid objects. We'll cover the next two lesser-known forces in more detail. Some spacecraft today are being designed with solar sails to take advantage of the Sun's steady solar wind to reach destinations far faster than conventional rocket technology. Each particle in an ejected cloud of material that was forming in an asteroid also felt this steady flow from the Sun. In space, rotating bodies and atmospheres in the presence of sunlight experience cyclic heating. Depending on the speed of rotation and other factors, this system has been shown to act like a Carnot engine, which produces a weak but steady thrust force that pushes or propels the rotating body away from the light source. Together, these forces acted continuously for centuries after the flood to accelerate these bodies and change their orbital trajectories. Finally, we'll also see how gases expelled from the fountains affected the orbits of clusters of particles as they passed through these dense gases that remained near Earth's orbital plane. Since all ejected material originated at Earth's orbit radius of 1 AU from the Sun, particles were attracted more to the gravitational center of the group of particles than to the Sun's. At first, these clouds of expelled dust, rocks, and gases were exceedingly large. The largest rocks launched into orbit about the Sun became the seeds that gravitationally attracted smaller nearby particles traveling with about the same speed and direction. That swirling collection of rocks, gas, and water ice caught in the seed rock's sphere of influence will be called a swarm, and was much like a swarm of bees with one difference. The gas in the swarm applied an aerobraking drag on the swarm's rocks so that the entire swarm slowly contracted, a process called aerobraking. This contraction of mass about the seed rock increased its mass and grew the sphere of influence, so that even more debris was attracted and joined the swarm. Eventually, swarms collapsed and became comets, asteroids, and TNOs, depending on their size, orbit, and water ice content. No sharp line separates comets and asteroids. In fact, some are considered both a comet and an asteroid. The larger asteroids spiraled out to become TNOs. A swarm's mass initially occupied such a large volume that its density was tiny. As photons of light radiated from the Sun, they struck these large clouds, transferring their momentum to the particles and gases. Photons from the Sun applied an outward force on the swarm. By outward, I mean away from the Sun, much like a steady wind would accelerate a low-density cotton ball. But there were two important differences. First, the swarm moved in the vacuum of space, so it did not experience the drag a cotton ball would receive in our atmosphere. Also, the Sun's energy heated the daylight side of the swarm, so the swarm's higher atmospheric pressure on the daylight side pushed the swarm outward. These acted collectively like a sail on a ship, so the solar wind gently but continuously accelerated the swarms of collecting particles far away from the Sun. This solar sail effect had the most impact on the swarm's velocity right after the flood, when the swarm's sail diameter was the greatest. Man-made solar sails are only a few feet in diameter. By contrast, swarms would have initially been thousands of miles in diameter, so they received tremendous momentum from the Sun's rays and over time traveled great distances. The energy from the Sun's rays can produce another effect for these small, low-density objects as they rotate in their orbit about the Sun. I specify small objects here as opposed to large, dense bodies like the Earth, which would see similar forces, but are so dense and massive that the effect on Earth's orbit is essentially zero. A fully intact small body is shown here for ease of illustration, but realize this effect also works similarly on loose swarms of rocks and gases as they rotated about a common center of gravity and slowly contracted to form asteroids. For any body in the presence of the Sun, there is a day side and a night side, which, if it is spinning, we can think of, as we do on Earth, as being split into times of day, 6 a.m. being dawn, noon being midday, etc. Of course, the length of time of this body's day would depend on the speed of its rotation, so the day's, quote, hours discussed here would not necessarily be 60-minute periods. The swarm's atmosphere on the day side is heated by the Sun, while on the night side the atmosphere loses heat and cools. The highest temperatures occur at what we might call 2 p.m. in the afternoon, while the coldest temperatures would occur just before sunrise on the swarm. A resulting force acts on the rotating body along this line. This force acts like a weak but steady and continuous thrust on the body. The difference between the heat absorbed and the heat rejected became thermodynamic work, that is, force acting through a distance. Force acting on mass produces acceleration in the direction the force is applied. This thrust force consists of two components in this case. The component that aligns with the body's orbital trajectory will increase the body's angular momentum, while the other component acts to increase the orbital radius of the body. Realize that while these vector arrows continuously change direction depending on the position relative to the Sun, orbit direction, and the body's rotational speed and direction relative to its trajectory, the resultant effect is always a thrust force away from the Sun. This change in trajectory is a bit hard to imagine, so it helps to see this animated in time. As the white thrust force arrow acts on the rotating body due to the cyclic heating effect from the Sun's rays, the path of the object is diverted from its initial trajectory and slowly drifts away from the Sun. We sometimes forget that there is no drag in the vacuum of space, so even though these forces were tiny, their continuous effect over centuries resulted in tremendous velocities and greatly altered orbits. Not all materials ejected from Earth during the flood were launched with enough velocity to become asteroid or comet swarms with large elliptical orbits. This low-velocity debris, mainly gases, maintained a circular orbit and remained near Earth's orbital plane since it generally matched Earth's orbital parameters. For a time after the flood, these gases were encountered every time a newly forming asteroid swarms passed through the inner solar system. Swarms on orbits with steep angles of inclination felt drag from these gases, so this too gradually made elliptical orbits more circular and acted to reduce their angle of inclination on every orbit cycle. As the swarm entered the inner solar system and encountered the gases, the drag acted on the swarm to slightly alter its trajectory to a flatter inclination angle. Remember, this would have happened for many centuries after the flood, so obviously the change shown here is exaggerated to see the concept more easily. Again, at perihelion, as the swarm encountered the cloud, trajectory was altered further, and the asteroid swarm's orbital plane progressively flattened as it was flung back toward aphelion. And so over the years, each asteroid swarm's initial inclination angles were reduced toward Earth's orbital plane. This is why today we observed a distinct asteroid belt rather than a spherical shell. From a polar view of the solar system, we can see how the combined effects of the solar wind and the debris cloud affected the asteroid orbits as they cycled in and out of the inner solar system. Elliptical orbits gradually expanded and became circular as these forces acted. As expected, the cloud of gases and debris near Earth itself had dissipated in the presence of the solar wind, so that today, after thousands of years, only a faint signature of interstellar dust remains. But how did the larger asteroids get all the way out beyond Neptune? To the casual observer, this probably seems impossible, so let me take a minute to explain. Whether an asteroid remained in the belt or continued to spiral away from the Sun was a function of the swarm's initial collective mass, which determined the amount of gases they could potentially collect and retain. Just beyond the asteroid belt, a tipping point was reached which distinguished asteroids from TNOs. Near the Sun, smaller swarms had a smaller sphere of influence and less gravitational pull, so they collected fewer gases and more easily lost the gases they did have to the Sun's rays. Once these smaller swarms lost their gases as they spiraled away from the Sun, they essentially lost their solar sails, and the solar wind had little effect on changing their trajectory, so these swarms ran out of steam in the asteroid belt region and became asteroids. Larger swarms with more mass had greater gravitational spheres of influence, so they were able to attract more surrounding material. A larger swarm's greater mass meant it was harder for the Sun's rays to impart the energy for the gases to reach escape velocities, so larger swarms held on to their surrounding gases. As each swarm spiraled farther away from the Sun, its gases cooled, so the gas was less likely to escape. So the swarm retained its solar sail and continued to spiral further and further away. So for these larger swarms, the Sun's energy could continue to act upon the swarm's still present gas, quote, sails, and pushed the swarm further and further away from the Sun. Since the time of the flood, these swarms have slowly spiraled out to their present orbits to become the TNOs of what is known as the Kuiper Belt. Because the swarms slowly spiraled out from the inner solar system, there was increased chance that some TNOs' orbits were perturbed by gravity as the giant outer planets passed by. This is why some TNOs' orbits are found to resonate with Neptune's orbit. This is only explained if the TNOs were once much closer to Neptune, as hydroplate theory proposes. The hydroplate theory of formation also readily explains why many TNOs, like asteroids, have moons, and why some pairs of TNOs of similar size have come to orbit each other as wide binaries. Wide binaries are pairs of TNOs of similar size that orbit each other, but at such great distances that their capture of one another is not easily explained. Professor Jean-Luc Margot explains the problem. Binary systems, two objects of similar size orbiting each other, are astronomical treasures for both the observer and the theorist. Their very existence raises perplexing questions about their formation, stability, and evolution. 7 such objects have now been identified in the Kuiper Belt. Such wide separations between are truly arresting and defy accepted ideas about the process of binary formation. How did such a system form? Why does it have such large orbital separation and angular momentum? Hydroplate theory's proposed theory of TNO formation again readily provides a mechanism for these strange wide binaries. Capture began during the flood, in the inner solar system when the bodies were much closer together. First, if the mass and size of the nearby TNO pairs differed greatly, and were within each other's sphere of influence, and a gaseous atmosphere was present, then aerobraking could occur and provide a means for the larger TNO to capture the smaller TNO as a moon. Or the smaller TNO may merge with the larger TNO. However, if a nearby pair were of similar size and mass, aerobraking would draw the TNO into tighter orbit and ensure that they remained within each other's sphere of influence. Similar size and mass of swarms would mean that they would each experience similar outward thrust from the sun's energy, so neither would outpace the other as they spiraled out. As the pair traveled to the far reaches of the solar system, the gases between the two TNOs dissipated, yet with so little mass out in the far reaches, there was minuscule chance that any other object could dislodge the pair, so the two became trapped in each other's growing spheres of influence. This may explain how binary pairs form, but how did the distance between the pairs become so great? Remember that as swarms of spinning rocks orbited each other and gravitationally collapsed toward their combined center of gravity as they traveled out from the sun, the combination of angular momentum of each swarm increased in keeping with the law of conservation of angular momentum. As a binary pair orbited each other, the more massive sides of each spinning TNO, represented here in orange, had more gravitational attraction to one another. This imbalance continually acted to reduce each TNO's rotational momentum over time. Again, in keeping with the law of angular momentum, this loss of rotational momentum was conserved and transferred to increase the angular momentum of the orbiting pair. So the pair naturally spun further and further away from one another. Eventually, the more massive ends of the TNOs oscillating relative to each other acted like pendulums until finally they became tidally locked, orbiting each other at seemingly impossible distances. The ejected sea of high-velocity debris, water, and gases from Earth during the flood also explains much of the Moon's surface topography we see today. The Moon is gravitationally locked so that only one side ever faces Earth. The smooth dark spots on the Earth side of the Moon were once thought to be seas, so were called maria. The dark maria are actually a remnant of a great deal of melted rock. The far side of the Moon is much different. While the Earth's side is relatively smooth, the far side is heavily cratered as though impacted by many small objects, primarily from debris kicked up by larger impacts on the Earth side of the Moon. Again, here is the view we always see from Earth, and here is the far side view that, while cratered, has no dark maria. While the Earth side is relatively smooth from the maria, the far side has been heavily cratered by many small impacts. The Earth itself tends to shield the Moon's near side from impacts. Did several asteroids impact the Moon while at the same time missing Earth? While not a complete impossibility, the expectation would be for large impacts to favor the far side of the Moon where it is not shielded by the Earth, or at least for impacts to be more evenly distributed about the Moon's surface. The far side of the Moon is always open to incoming impacts. We might imagine that with the Moon being so far away from the Earth, that the Earth would be a poor shield for the Moon's near side. That is because we tend to think of shielding in terms of straight-line impacts, somewhat like seeking cover from bullets. So in this scenario, there seems to be many available angles where incoming objects could still strike the near side of the Moon. However, unlike bullets at short range, the large gravitational pull of the Earth greatly affects trajectory. The Earth's gravity makes striking the Moon's near side by first passing nearby the Earth much less likely than we may first imagine, even though the Moon is physically far from the Earth. The shielding effect of Earth's gravity becomes even more apparent when we remember the concept of gravity being a function of an object's mass, which stretches the fabric of space, making a gravitational well. When this concept of gravity is visualized, we can more easily see how unexpected it would be for an object rolling left to right on the gravitational well to strike the near side of the Moon. It is possible, but certainly a great deal less likely than striking the far side. Inbound objects moving right to left have a much better chance of striking the Moon's far side. What if the debris that struck the Moon's near side came from Earth? Gravity measurements of the Moon's surface confirm several areas of highly concentrated mass, likely due to very large objects that impacted from the direction of Earth. If these were random asteroids from space, why are they all concentrated on the Earth side of the Moon? How did several asteroids impact the Moon while at the same time missing Earth?
Assuming the Moon is billions of years old, researchers find that the Moon remains unexpectedly hot, measuring very high heat flux still emanating from its surface, and finding a small molten core.
In addition, the Lunar Prospector picked up signatures of the short-lived radioisotope radon-222, emanating near two craters on the Moon's leading face. How did radioactivity develop inside the Moon? Hydroplate theory proposes that the mass concentrations, the unexpected heat, the presence of radon-222 gas, the remnant water ice in craters, and the unique topography differences between the Moon's near side and far side are best explained as a result of a recent bombardment of the Moon during the flood as materials were launched from the Earth's deep fountains. Dr. Robert Brown, professor of astronautics at the United States Air Force Academy, calculates that the debris would have reached the Moon's sphere of influence outlined in yellow approximately 5 days after exiting Earth's atmosphere. Ejected debris then began impacting primarily on the leading face of the Moon's near side.
As discussed in the hydroplate overview and radioactivity presentations, the ejected materials would be expected to contain both water and many radioactive isotopes, some of which continue to decay into short-lived radon gas today. The recentness of this flood event explains why these short-lived materials are still detected on the Moon's surface. After millions of years, short-lived deposits of ice in these craters would have long since dissipated.
Hydroplate theory also explains why the far side of the Moon does not have mass concentrations, or mascons, nor the dark maria that we see on the Earth side. The far side was sheltered from direct impact. However, smaller, lower velocity debris lifted from the surfaces of the near side's direct heavy impacts could not escape the Moon's gravitational sphere of influence, which pulled it back. This produced many secondary impact craters all around the Moon's surface. These secondary impacts would have struck the near side of the Moon as well. However, since the Maria basins remained hot and volcanically active for a time after the initial impactors hit, many of the secondary impacts on the near side were absorbed and quickly resurfaced, while the cold, inactive far side's surface preserved the many craters. The added mass from these impacts would have changed the Moon's orbital characteristics from what they were in the past. History shows that ancient calendars held that a month was once 30 days rather than the 29.53-day lunar month today. Many ancient cultures held to a 360-day year as well. References in Vedic and Sanskrit works explain that the year and month changed due to great upheaval in the past. Genesis 1:14-18 indicates that the original purpose of the Moon was for telling time. The flood account in Genesis 7 also indicates that before the flood, months were exactly 30 days. We'll not cover it here, but I explain how the flood changed the year to 365 days in Part 6 of the Hydroplate Overview series. The added mass from these impacts on the Moon would have changed the Moon's orbital characteristics. If the Earth had originally had a 360-day year and the Moon originally had a perfectly circular orbit with a 30-day period, then this system would have made for an excellent method for observing time. Assuming this perfect orbital condition to be the original orbit of the Moon, Professor Robert Brown has shown that if only 1.22% of the estimated mass of debris launched during the flood were captured in the Moon's sphere of influence and eventually struck the Moon, it would have reduced the Moon's angular momentum, dropping the Moon into a lower orbit, and the lunar period would have decreased to what we observe today. In fact, analysis of this proposed scenario of added mass shows that the resulting calculated perturbations of 7 orbital parameters of the Earth-Moon system match almost exactly with what is observed today. Note that there is only a fraction of a percent of error between the actual observed values of the Moon today versus these calculated parameters. This information, taken in conjunction with the many ancient historical writings that suggest there used to be a 30-day lunar month, make for a compelling argument that the initial created condition of the pre-flood Earth-Moon system was indeed a very good system for measuring time, as indicated in Genesis 1:14. The full analysis and derivation of these results may be reviewed at the link shown here. Sometimes people ask, If comets are really from Earth, couldn't you just calculate orbits of all the comets backward from today and then see them all converge near the Earth at the same time of the flood? Unfortunately, comet orbits are changed to varying degrees when they pass near a planet. The closer the pass and the more massive the planet, the greater the change. If a comet, 1, seldom comes near a planet because its orbit takes it far from the planets most of the time, and 2, has been observed many times in the past 2,000 years, so its orbital path is reasonably well known, and 3, powerful computer programs have projected it and all the planets back 4,000 to 6,000 years ago to try to calculate how these inevitable perturbations have altered the orbits, then we should find these comets near the Earth at about the same time the flood began. So in spite of these challenges, however, 2 comets best fit these requirements: Comet Swift-Tuttle and the most well-known comet, Halley's Comet.
Perihelion for these 2 comets is very close to Earth's orbit. However, as you can see, rarely will they both be close to the Earth at the same time. Using the many historical observations of these 2 comets does allow us to analyze statistically when each would have been near Earth at perihelion, by projecting their periods back in time. The statistical approach of analysis also allows us to keep track of the total error in our conclusions. So does this method result in showing these 2 comets and Earth, all 3 bodies, once occupied the same relatively tiny volume of space? If so, is that just a coincidence? This graph plots the closeness in days that the 2 comets would pass perihelion near Earth's orbit as the analysis marches their earliest orbital periods back in time. So for example, 4,200 years ago, Halley's Comet and Swift-Tuttle's perihelion times were roughly 22,360 days, or about 61 years apart. 4,400 years ago, their perihelion separation was much closer, roughly 949 days, or about only 2.6 years apart. So as you can see in the zoomed-in area of the slide, from the time one comet passed perihelion, it was 2.6 years until the other comet passed its perihelion. This is closer than 61 years, but when we consider we are looking for an event that occurred within a few weeks or at most months, 2.6 years is actually a very loose clustering, with one of the comets being well outside Jupiter's orbit. Interestingly, continuing to go back in time, these 2 comets do not cluster significantly close to Earth at all. That is until you go back to around 5,300 years ago, or 3290 BC. Amazingly, the analysis, using the comet's earliest known periods based on the earliest observation, shows that inside of the year 3290 BC, both of these very clock-like comets passed perihelion near Earth within just 35 days of each other. At our current timescale of 2 seconds a year, it is hard to see and appreciate how close these 3 bodies were to each other in such a short period of time. To see this more clearly, we'll slow the animation so a year equals 24 seconds. Now at this much slower pace, we can see Comet Swift-Tuttle enter near Earth's orbit and pass its perihelion. Then within only 35 days, Halley's Comet passes perihelion.
Of course, each comet's period would have changed slightly with each orbit due to gravitational perturbations from other large orbiting bodies like planets, just as is observed today, so there is some uncertainty as to the actual time that this occurred. However, the odds of a comet receiving a boost from another object are the same as the odds of the comet feeling a drag, so the error distribution is expected to be a normal bell-shaped curve. Again, the historical record of these comets passing by Earth gives a suitable sample of data that reveals how each comet's period changes over time, and this can be used to show the expected error in the 3290 BC mean date. Statistical analysis of these 2 comets results in a 1 sigma standard deviation of plus or minus 100 years from the mean date. As you can see, no matter where Earth was in its orbital path, this is still a fantastically close clustering of these 3 bodies in 3290 BC. But is this statistically significant, or just a random but very common occurrence? In other words, how often does a deep spike in the data similar to this 35-day clustering occur? Well, statistically it turns out that if the orbits were just random, then we'd have to search forward or backward in time an average of 333,000 years in order to find a clustering event that was at least as close as the 35-day event that occurred 5,300 years ago. If this data were printed on 8 by 11 copy paper, and you printed out 2,000 years of data on each page, you would have to print out 176 pages of data before you found another spike in the data that was as deep. Or another way to visualize the rareness of this event would be to watch the opening slide of this section that was running at a rate of 4 years per second. We would have to watch the animation at this speed an average of just over 23 straight hours to see the tight clustering occur again. So a very unusual and rare event indeed. Statistically, it is unlikely that this is simply a coincidence. Considering all we've just covered in running the clustering event forward in time roughly 5,300 years ago, we see that the more likely scenario is that during the first weeks or months of the flood, clusters of material that eventually formed into these two comets, and all other comets for that matter, were launched during separate powerful pulse events from the fluttering crust of the Earth. Follow this link for more information on this statistical analysis methodology and how the Greek Septuagint translation of the Old Testament genealogies comes surprisingly close to matching the time of Noah and the flood to this astronomical data. This concludes our sidebar discussion of hydroplate theory's explanation for the formation of comets, asteroids, and TNOs.